Those of you coming in late, no, this had nothing to do with biology. Just playing. So, Brumfeld, not here yet. Well, we still got 5 minutes, but some Champion is here. WVSU here. Gorby, not here. Gross is, I think, online. If you're online and I say your name and you're not here, don't worry about it, because you're just gonna, as far as we're concerned, you're not here until you send in those attendance words at the end of the lecture. So, again, if you're online and I see you're not here, you don't need to correct me. Anyway, Gunther is here. You wearing WVSU stuff, Gunther?
Yeah.
All right. Lecture credit to WVSU Wednesday. Same as Hill. Not the other Hill. Jackson? Not yet. Keys is here. WVSU here. Perez is not here yet. Sigmund, I think, is online. Slaughter is here. Regular close in the WVSU stuff. Just checking. Smith is not here yet. Stover is here. WVSU here. Tompkins also representing state. Nest is not here yet. Watson, I believe, is online. I don't remember for sure. Young is here. Zweiback is here. Is that a WVSU thing? Sometime before this semester, I'm going to have my glasses. I'll actually be able to see. Lawrence is not here yet. Carter is here. And Nest just came in. WVSU here. Excuse me. Yeah, so for those of you who are online, it'll be sort of like when you're in person, except instead of having the option of sending the words, you're going to need to send the words. But since you're streaming online with us, you do not have to send screenshots. So just send the list of words. You probably want to do it right away because you're going to need to be here by 9 a.m. for lab. So hopefully if you're online right now, you're just avoiding my sickness. Morning. Is it Gorby?
Yes, sir.
All right. Is that WVSU hat? No, just checking. Okay.
No, sir, sorry.
No need to apologize. It's just WVSU Wednesday, as I call it. And anybody happens to be wearing WVSU stuff on Wednesday, you get a few more attendance points. Still got a couple minutes. But just as a reminder, since I'm hearing the door jiggle, I decided to start locking the doors for safety reasons. Call me paranoid, but the world's a little bit crazy. So these doors you have to bust them in to open them. So that'll buy us some time. Also, we could slide all these desks to the door. And that glass has little metal stuff in it, like chicken wire. So it's not like they can just easily bust through and get in. So pretty secure room. All right, from the top, Brumfeld is here. Champion is here. Gorby is here. I believe Gross is online, but I don't know for sure. We'll find that out later. Gunther is here. Both Hills are here. Jackson, not here yet. Keys is here. Perez is here. You wearing WVSU stuff by any chance? Okay. Sigmund, I believe, is online, but I'm not sure. Not here. Slaughter is here. Smith is here. Stover is here. Tompkins is here. Nest is here. Watson, if I remember correctly, is online. Okay. Young is here. Zweiback is here. Lawrence. Lawrence is not here. Wilson is here. Did I miss anybody? All right. It's 8 o'clock, but I'll give it until 8:01 before anyone's officially late. So I guess I'll just do the usual reminders, because if they came in late and missed this, it should be okay, because I say this every day. So to remind you, attendance is mandatory and graded. And again, you might be wondering, why does he say it every day? You'd be amazed at how many people at the end of the semester who their grade is hurt from attendance, and they say, I didn't know. A lot of stuff they'll say, I didn't know. So in case you're wondering why I repeat myself so much, that's why. Not just with attendance, but other stuff too. So anyway, yes, attendance is mandatory, it's graded. If you have a lot of absences, get in touch with me. You can go back. Most of these videos, lectures have been recorded. We have had some technical difficulties, but you can make up for your absences by watching those videos and following the directions of the videos. Speaking of which, for the video, for the rest of you guys, the first word for attendance today is going to be Constitution. Today is Constitution Day. So Constitution is the first word for attendance. As usual, those of you who are here do not have to send in those words, but if you do, send them in before 9 a.m., you can get some extra credit. For those of you who are online with us currently, as it's streaming, same for you. Well, you do have to send in the words, but you do not have to do any screenshots. Just send in the words before 9 a.m. If you're watching a video at a later date, you also have to send in the words. But again, you will, in addition to sending in the words, you need to send in a screenshot every time I say one of the words. And again, the first word is Constitution. So that's it for attendance. Any questions about attendance? All right, just to remind you, exam 1 is behind us, but you can retake it. You can retake it as many times as you want. It is untimed. It is open book. So we just keep going. I will not change your grade until you tell me to change your grade. I won't know that you've retaken it. I have no way of knowing. So that's the other catch. You have to let me know that you're ready for me to change your grade. So if somehow you keep retaking it and keep getting a lower grade, which I don't see how that would be possible, just don't tell me, and I won't adjust your grade, and we'll stick with your higher grade. So any questions about the exam 1 retake? Okay, lab today is at 9 a.m. as usual. Make sure you're here on time. If you don't have pants like me, like some other people, make sure you have pants and closed-toed shoes. So if you need to leave the lecture a little bit early to do that, I guess go for it. Me, I'm sick. So I'm going to get you guys set up with lab, and then I'm leaving you in the hands of the TA because I don't want to be walking around helping you and breathing on you. So I will be gone. Actually, I'm not going to be gone. I'm going to be in the office. So that being said, too, when you're in lab, if you need my help, if for some reason the TA is not helping you or whatever, or you prefer my help, just come to my office and I'll help you. Any questions about lab today? All right. There's no pre-lab this week, as a reminder. So there's nothing due on Friday, well, other than the lab that we're going to do today. There's no pre-lab due this week because next week is just going to be a pre-lab lecture. So next week, make sure you're here because that's the only way you can get points for next week's lab. 20 points just for being here on time and not leaving early. So any questions about that? All right, Google Drive. This isn't from you guys, but for my online classes, I've been having a lot of issues with some of the students. So I just want to remind you, everything is set up on Google for a reason. So for example, when you open up a lab, right, and then you make yourself a copy, it's then saved to your Google Drive. You never have to open it up again. You never have to make another copy. It's there. So that means no matter what device you're on, you just get in there, go to your Google Drive, and open it up. I have one poor lady who's got me. Every time I met her online to help her with a lab, and she was sharing her screen. She had like 20 copies of the same lab because every time she went in to do it, she would open up and make herself a new copy. You don't have to do that. If you need help with Google Drive, let me know. I actually did that to make things easier for you guys, not harder. So let me know if you need help with that. Any questions about Google Drive? All right. Also, as always, check your course emails and your announcements every day. That's a little bit less important for you guys than the other students, the online students, because we at least get to see each other 3 times a week, 4 times a week if you include that. So, anyway, any questions? All right, nice and easy. So again, I know I already said it, but the first word for attendance is Constitution. So let's get started. We were leaving off talking about basically stuff coming in and out of the cell, right? First we talked about what the cell membrane is made of. Then we talked about, I might have to get one. All right. So we were talking about how it's obviously very important for a cell to control what comes in and out of it, right? So we talked about passive transport, which included diffusion, right? Diffusion is when things just come in. It doesn't require an input of energy, hence passive transport. We also talked about osmosis, which was also a type of passive transport because it is a type of diffusion, specifically water diffusing across the membrane. Then we talked about active transport. Active transport is when we use proteins embedded in the cell membrane to let things in, and that does require energy. usually in the form of ATP, hence the name active transport, right? It requires energy. You're pumping things against the concentration gradient when we're talking about active transport. And to remind you, active transport and diffusion will be important later in the next chapter when we start learning about how photosynthesis and respiration works. None of that would happen if we didn't have diffusion and or facilitated diffusion and active transport. So that leaves us with this. This is the last big discussion about things coming in and out of the cell, and then we're going to jump into chapter 4. So here we're talking about big stuff coming in and out of the cell, right? So previously we were just talking about things like diffusing directly through the membrane, or perhaps we had a protein and it would come little things coming in and out of the membrane. Now we're just talking about a large volume of stuff coming in and out of the cell. And the first thing you're going to learn about is endocytosis. This is another type of active transport. So again, this requires an input of energy. For extra credit, you can look that up. The book doesn't mention it, so I'm not either. What kind of energy does it need to do this? But what is it? Hopefully the name will indicate, because I'll go ahead and spoiler alert, the next one you're going to learn about is called exocytosis. You're going to need to know the difference between the two. Hopefully the prefix is given away, right? Endocytosis is stuff coming in. Exocytosis is stuff coming out. The only thing that makes it slightly trickier is endocytosis is also broken down into two subcategories. There's phagocytosis and pinocytosis. Does anybody know what Pinot Noir is or Pinot Grigio? Has anybody ever heard those terms? What is it? No? Wine, good. Pinot Grigio, Pinot Noir, that's a wine. What are you supposed to do with wine? Drink it, right? When I say supposed to do, I mean, anyway. So yeah, you're supposed to drink it. So when I was a student, that's how I remembered pinocytosis was like bringing in liquids. It's cellular drinking, so to speak. I always remember, okay, Pinot Noir, Pinot Grigio, there's probably other Pinots, but I just think, all right, wine, you drink wine, therefore that's cellular drinking. Now when I say drinking, again, just to be clear, even though I'm talking about wine, that doesn't mean like alcohol, right? It's just any liquids. When a cell's bringing in any liquid, it's called pinocytosis. And then there's phagocytosis, which is basically, as you might imagine, if one's eating, is drinking, the other one is eating. Right? So that's when the cell engulfs a particle that's packaged in food vacuoles. But again, mostly for the exam, we just know that phagocytosis is bringing in solids, pinocytosis is bringing in liquids. And your textbook goes into detail. I don't think this picture's from your textbook, but I think there's versions of this in your textbook that shows how it happens, right? All this stuff comes in, and then the cell membrane, because remember, it's a phospholipid bilayer, it kind of engulfs it until you get a little vesicle pinched off, and that goes into the cell, and then it goes to wherever it needs to be in the cell. So that's endocytosis. Any questions about that? Nice and easy, right? All right, and again, for the exam, I'm not going to ask you about the cell engulfing particles or packaging it in a food vacuole. For the exam, you need to know that endocytosis is a type of active transport. It's bringing in a lot of stuff at once instead of a little bit. And you need to know the two different types of endocytosis, or phagocytosis, which is eating, so to speak, and pinocytosis, which is drinking, so to speak. And also, I put a little star next to that, reminding me that this is not in the textbook. So if you're taking notes, you might write that down. So when you're studying this particular thing, you're going to want to use the slide. Because as you guys know, for this 100 level class, I like to teach out of the textbook. So there's very few times when I'm going to test you on something that's not in the textbook. This is one of those few times. So any questions? All right. Exocytosis, I'm going to give you a little bit of information, but basically all you need to know is it's kind of like the opposite of endocytosis. Exocytosis is still a type of active transport. Still, we're talking about moving a large amount of stuff, molecules or large molecules, but now it's leaving, right? So it's kind of like that picture we saw earlier, but now it's the opposite. Here we have this vesicle filled with stuff, whatever that stuff may be. That vesicle merges with the cell membrane, and it just kind of plops it out. So there you go. That's endocytosis and exocytosis. Another extra credit paper you could write is why. Right? Why do cells do this? Or why or what, I guess. Because here I said traffic of large molecules. So which large molecules, right? You look that up and say, all right, well, if it's starch, it uses this. If it's water, it goes directly through the membrane, whatever it may be. Any questions? All right, if you download the PowerPoint, you can watch this little animation that shows pinocytosis in action. That's that. I'm going to start the next chapter now. Does anybody have any questions about chapter 4? And to remind you, most of chapter 4, when we talked about how cells work, that part was not very important as far as the exam is concerned, because again, you're going to learn about how cells work from here almost to the end of the semester. Now that we're done with the background stuff, we're finally getting into the real meat and potatoes of this semester. You're going to learn how cells work. And from there, you're going to learn all that stuff I previously showed you and introduced you to, all these different parts and functions of the cell. Now we're going to focus on specific parts and specific functions. So here we go. This is chapter 4, how cells obtain energy. And I'll go ahead and tell you this, just so you know, mostly exam 2 is going to be about this chapter and the next chapter. Yes, there's going to be a little bit from the last chapter when we talked about, all the different types of diffusion and osmosis. But most of this exam coming up, well, not coming up, it'll be about a month. Most of exam 2 is going to be about energy. And if you remember from chapter 1, that is one of the properties of life, right? Is the transformation of energy. Life transforms energy. Life needs energy, and it has to transform it from one form to another. So that's what we're going to talk about. So speaking of which, before we can even get into how the cells do this, I'll get you a little background information on what energy is, what metabolism is. Then we'll start talking about how it works. So here are the learning objectives for this chapter, or this portion of the chapter. By the end of it, you should be able to explain what metabolic pathways are. And that'll be useful for the exam. You might need to know that. You'll need to know the state. You'll be able to state the first and second laws of thermodynamics. You will need to know that for the exam. You'll be able to explain the difference between kinetic and potential energy. You'll need to know that for the exam. You'll need to be able to, or you will be able to describe endergonic versus exergonic reactions. Again, you'll need to know that for the exam. And then by the end, you should be able to discuss how enzymes function as molecular catalysts. And once again, you need to know that for the exam. So as far as like exam-worthy stuff, this is a very important chapter and section. 4.1 is just full of stuff that you need to know for the exam. So for that reason, I am going to try to go a little bit slow. If I go too slow, let me know. Maybe I can speed things up. First of all, there's this word bioenergetics. I'm going to put a question mark next to this. I'm not sure if I'm going to ask you that on the exam. Basically, bioenergetics is what we're about to talk about. But again, I might not just use that word and that term in the exam. But it describes the concept of energy flow through living systems. So again, like I said earlier, chapter 1, when we talk about those properties of life, the things that make something alive, energy transformation was one of them. Right? Energy has to flow through these systems. And what do I mean by systems? Well, remember, we started very small and we got bigger, right? So first, we talked about atoms, which we talked about. You bring a bunch of atoms together, we have molecules, which we talked about. Bring a bunch of molecules together, we get organelles, which we talked about. All those things require energy. And now, again, we're still about to talk about some organelles. We're also going to talk about cells in general. And again, we're going to talk about energy flow. And then later in the semester, we will talk about not just cells, but whole organisms and populations of organisms and ecosystems and things like that, terms that you're going to be familiar with later. And even then, we're still going to describe this concept of energy flowing through the system. The flow of energy is through a series of chemical reactions. We'll talk a little bit about that later. So in a sense, that whole point is more like an introduction to what you're about to learn. All chemical reactions that take place inside of cells are known as metabolism. So that's a term you should know. It's all the chemical reactions that are happening inside your cell. And really, chemistry is what keeps us alive. It's these chemical reactions that are happening inside the cells that are keeping us alive. You'll see what I mean. There's this imbalance. Your cells produce this imbalance just so that your cells can try to balance things out. Remember, that was another property of life in chapter 1, was this idea of homeostasis, right? Trying to keep things balanced. Well, cells will purposely make things imbalanced just so they can naturally try to balance things out, and that's how we get energy. Long story short. So any questions about this slide? All right, so again, all these concepts are important. But the name bioenergetics, again, the question mark next to that because I'm not quite sure I'm going to test you on that term. But these concepts, it's a preview of what we're about to talk about, and they are important. And this is a great little picture from your textbook, right? So ultimately, with a few exceptions, all energy on Earth comes from the sun, right? Either in the form of heat or light energy. There's also some other stuff that we don't even get into, but mostly heat and light. Yeah, and mostly all comes from the sun. And that's a good topic for an extra credit paper if you want to look into it too. What are the few exceptions to that rule where life gets energy not from the sun? Ultimately. Now, directly, there's a lot of things. For example, a mushroom might decompose something and never see light in its day. It's not getting its energy directly from the sun, but it's decomposing something that was alive, that probably ate some kind of plant, or maybe it is a plant, and that plant ultimately got its energy from the sun. So I don't mean directly from the sun, but ultimately. Most things ultimately get their energy from the sun. Even like wind power, for example. That's the type of energy, right? You've got the wind, it turns the turbines, you make electricity. That is another example, though, of heat energy. Sun heats up the earth, parts of the earth get hotter than other parts, that causes wind, that causes kinetic energy, and that we transfer that into electric energy. Not that you need to know that for this exam, but just good examples. So any questions about this slide? All right, the next word for attendance is Billy, like the name Billy. Today is Billy the Kid's birthday. All right, 2 metabolic pathways that you need to know. You need to know the difference between them. Anabolic versus catabolic. Anabolic needs energy because it's going to be stored in a new molecule. So in other words, anabolic is building stuff, as you can see from that picture down at the bottom, right? At the bottom, we've got these 4 molecules, I guess we want to call them that. And remember when we talked, I think it was chapter 1, maybe even chapter 2, I said, it takes energy to build molecules. And that's what anabolic reactions are. They're building molecules. And it takes an input of energy to do that. Because a lot of times, as you hopefully remember, the outside of an atom is covered with electrons. Electrons are negative. So in a sense, a very basic way of describing things, and it gets a little bit more complicated than this in real life, but in a very basic way of thinking of that, you could think of like these atoms don't want to be together because they're repelling each other because they're all covered with electrons, which repel each other. So it's going to take energy to squeeze them together. Some more than others, but we don't even get into that in this 100 level class. So that's anabolic pathways. Any questions about anabolic? Who has heard that term before? Anabolic. You probably heard. Yeah, where'd you hear it from? Steroids. Yeah, steroids. So when people take anabolic steroids, it's to get bigger, right? Whether because they're abusing it, to make themselves look bigger, or maybe because they're sick and they have to take anabolic steroids because whatever they're sick with is destroying their tissue, so therefore they need to take these anabolic steroids to help them rebuild it. So yeah, if you can remember anabolic steroids and people abusing them to make themselves look bigger or hit a baseball farther, hopefully that'll help you remember that anabolic is the type of metabolic pathways that's building stuff. Which, a little throwback to chapter 2, that would be a dehydration reaction, right? When we're bringing things together, it's a dehydration reaction. All right, so the opposite of that is the catabolic reaction. This produces energy as the old molecule is broken down. So imagine these are the same molecules, right? Imagine this is a circular cycle. That's kind of redundant. But anyway, we've got these 4 molecules. It takes X amount of energy, and there is a known amount of energy for every reaction. It takes a certain amount of energy to put them together, right? And then later, if we wanted to, we could take this molecule, this 4-atom molecule, right, and break it down. And however much energy was used to build that, that's how much energy is going to be released. And that'll be an important concept in this chapter. Lucky for you, this is only a 100 level class, and it's biology and not chemistry, so we're not going to quantify that. So when I say however much energy is used to build it, that's how much energy is used to release, or is released when you break it. That's the end of it. In real chemistry, you would do the math and have to account for it and calculate it. But here, we're just know that it's equal. Either way, whether we're talking about anabolic or catabolic, you're going to need enzymes to make it happen. So remember, you were introduced to enzymes in the last chapter when we talked about proteins. As far as we're concerned in this class, all enzymes are proteins. There are a few exceptions, but that's what they do. And remember, proteins are all about their shape, right? So these enzymes, as you're going to learn later in this chapter, it's all about their shape. It's almost like a lock and key. They fit molecules together to either build them up or break them down, but it's all about the enzymes, which will be important even later in the semester. So again, just as a spoiler alert, later in the semester when we learn how we go from DNA to RNA to protein, that's not trivial, right? Because you might just think, okay, so big deal. Now I know how a cell makes protein. Keep in mind, again, enzymes are proteins, and enzymes are basically making every single chemical reaction happen in your body. So without all that, you wouldn't have these chemical reactions and you just wouldn't exist. So that's why proteins are so important, because again, it's without these enzymes, we basically wouldn't be alive. So any questions about this slide? All right. Here's a term I might ask you, but probably not, because there's two different laws of thermodynamics, and you're going to need to know those, so you might not need to know this definition. The thermodynamics, that's the study of energy and the energy transfer involving physical matter. In other words, all that stuff I was talking about earlier, that's thermodynamics. When I'm talking about all the energy it takes to build that molecule, and then all that energy can be released when you break down that molecule, that's thermodynamics. So what is energy? You need to know this. Not only for the exam, but because this concept is important, you're going to need to know it mostly throughout the semester. Energy is the ability to do work or to create some kind of change. That is what energy is. So think about electrical energy, right? Electrical energy can do work. Like when I put that battery in the back of my weed eater, that's doing work, it's turning the thing. Or electricity can create change, right? So it was a little bit warm when I came in this morning. Turn the thermostat, the electrical energy was converted to other forms of energy and changed the temperature. There's some different examples. You definitely don't need to write all these down because only some of them are important for this semester. Electrical energy, I use it as an example all the time because we're all familiar with it, but as far as this chapter is concerned, or this semester is concerned, it's mostly not important. Heat energy, that one's relevant to us. Light energy, that one's relevant to us. Chemical energy is very relevant to us. And again, all the relevant ones we're going to talk about moving forward. And there's other forms of energy too. So if you want to look that up for independent, or I keep saying independent work because that used to be what it's called. If you want to look up some other forms of energy for extra credit, you can. And again, if you're writing an extra credit paper, there is no limit to how long it could be. It could be a couple sentences. I looked it up, and according to this source, here's the other forms of energy, right? Nice short paper. Of course, the longer it is, the more points you get, but it's all extra credit anyway. So if you turn in something to get half a point of extra credit, you know, that's going to do nothing but help you. Anyway, so any questions about that before we move forward? All right, the different laws of thermodynamics, you need to know these. The first law of thermodynamics states that energy can be transferred from one form to another, but it cannot be created or destroyed. It's very important. And if you really think about it philosophically and look at the big picture, that's kind of mind-blowing in a way. Because in a sense, that's saying all the energy in the universe, since it was created, however it was created, from that moment on, that's the amount of energy we have. It might be transferred from one form to another, but that's it. That's our finite amount of energy. That's what current understanding tells us. Let me remind myself what this little star is. Okay, so I left myself a little note. Your textbook defines it a little bit differently. So this is the definition from the old textbook. So this is a good reminder. When it comes to vocabulary words, you don't need to memorize them verbatim. If you just know the words and can spout them off, they don't know what they mean, then that's useless. So just understand what the concept is, right? So again, for the first law, we're just saying energy can be transferred from one form to another, but we can't create it and we can't destroy it. Meaning when we do chemical reactions, we're not really creating energy, right? Or, depending on the chemical reaction, we're also not destroying it. We might lose it from our little system, right? So again, using John Amos electricity as an example, it burns coal, that releases heat. That heat is then used to steam, boil water, and then steam turns the turbine, whatever. So John Amos does lose a lot of energy in the form of heat, right? A lot of that heat escapes. So John Amos may have lost that energy, but the universe did not. That heat energy was then passed off into the atmosphere of Earth, which will eventually trickle out into space. And that's a whole different discussion that we don't even have in this course. So life depends on this conversion of energy from one form to another. So once again, as a reminder of why this is important, like we said in chapter 1, one of those properties of life is this energy transformation, right? We can't have energy without being able to transform energy from one. Can't have life without being able to transform energy from one form to another. So that's the first law. Any questions about the first law? Right. And again, don't memorize it verbatim. Understand the concept. Second law, same thing. Don't memorize it verbatim. Understand the concept. Energy is lost as it is transferred from one form to another. So again, when I say lost, because we know it can't be destroyed, when I say lost, I mean it's lost to that area. So if you fill an AC adapter, for example, like you plug something into the wall, and the wall and the electricity coming out of the wall is AC. Sometimes electronics require DC, so there's a little thing that changes it from AC to DC. It's converting it from one form to another, and that's why they're a little bit warm. Because we're converting energy from one form to another, and that releases heat. And of course, if you fill one and you can't feel it being warm, that's a good thing, because that means it's doing it very efficiently. It's still giving off heat, you just can't perceive it. That's a good thing. Anyway, any questions about the two laws of thermodynamics? All right, let's talk about these pictures really quickly. So here we have chemical energy being converted to kinetic energy. If that picture doesn't make sense to you, what we're getting at here is these kids maybe had an ice cream cone, they ate it. There's a lot of chemical energy in the molecules in that food, right? And then through catabolic reactions inside these kids, they broke down those molecules and used energy, and then they're converting that energy to kinetic energy, because they're going to move around on the bicycle. And of course, here we have the ultimate one. Here we have this light energy from the sun. We've got this green leaf that takes that light energy and converts it into chemical energy. Anyway, any questions? All right. So we've talked about this before. Let's see if anybody can remember. When we're talking about heat on the molecular level, what is heat? Like when I say something's getting warmer or getting colder on the molecular level, does anybody remember what I mean? It's a very important concept. No one remembers? All right, here's what you need to know. Heat is a type of kinetic energy. Like I mentioned earlier in the semester when we talked about temperature change, when we talked about the properties of water and how it can regulate temperature change, we mentioned that when we say temperature change, what we're talking about is the movement of molecules. So the faster things are moving, the warmer things are. The slower they're moving, the cooler they are. So that is heat. Heat is a type of kinetic energy. It's the random motion of matter. Not that you need to know this, but your textbook points it out, and it is important if you were taking like a more advanced class, but for this class it doesn't matter, I'm only going to mention it. But heat is the most chaotic and disordered form of energy. Again, you don't need to know that for the exam, I'm only mentioning it because it was in the textbook. And again, for people doing more advanced science, that would be important. For us, it doesn't really matter. And again, just to remind you, all energy conversions generate some heat. So when you convert energy from one form to another, it's going to put off some kind of heat. Then there's something else very important for advanced science, but not for this class. So I'll put a big old X through here for the whole thing. Again, your textbook mentions it, so do I. Entropy. This is a measure of disorder or randomness in a system. So every time energy is converted from one form to another, entropy increases. And I'll just leave it at that. Again, this is a very important concept if we were doing more advanced science, because there's all this stuff we're talking about, there's formulas for this, mathematical formulas. And we're not doing any of those. We're just talking about the concepts. But if you were doing the formulas and accounting for everything mathematically, then entropy would be important. That's an important part of the formula. So would heat. But again, for us, we're not doing formulas, so it doesn't matter. All right, there's two different types. Well, there's more than two different types. But if we're talking about, there's two basic types of energy. You've probably heard it throughout your life. What are the two basic, these pictures hopefully give you a good hint of what I'm about to talk about. What are the two basic types of energy that you've learned about? And these two different pictures, they're both showing water, right? But this one's showing one type of energy. This one's showing a different type of energy. Any guesses? No? All right. Kinetic energy is the first one. We've already mentioned. Kinetic energy is the energy of motion, right? So that's this right here. All that water flowing downhill, that's kinetic energy. Of course, the opposite of that is potential energy. That is stored energy. So like this dam, right? This dam has a lot of stored energy. Gravity is trying to pull that water that way, but it's being stopped by the dam. So there's all that stored energy. When it's released, like if you open it up or if the dam were to break, that would turn into a lot of kinetic energy, right? That potential energy would then be converted to kinetic energy as the water was released from the dam. Now, as far as we're concerned, potential energy is more important. And by we, I mean us studying this in biology, right? As far as this course is concerned, potential energy is more important. So I'm sure most of you are familiar with this old thing. This is how I learned kinetic or potential energy when I was a kid. If I said, okay, which one has more potential energy right now, the black marker or the pink one? Which one has more potential energy? And I hope you guys are just shy. There's no way you got through school and didn't see this analogy before. Which one has more potential energy, the black one or the pink one?
Black.
Black one, good, good, good. Because it's higher, right?
Correct.
So when it hits the ground, if I drop these both, this one's going to hit the ground with more energy than this one. So yes, that's the common thing that I was always taught. But that type of potential energy, for this class anyway, is not that important. For us, and that was location, right? That's what I was describing with location. The more important one for us for the potential energy is structure. So when we talk about chemical energy and all the energy that's built, put into those molecules, like when you build it, that's structure, right? That's potential energy by the way we built those molecules. So that's the one we're going to focus on a lot. But nonetheless, you need to know the definition of both for the exam. Kinetic energy, energy of motion. Potential energy is stored energy due to its location or its structure. And again, for us, we're going to be talking more about the structure. Nonetheless, here's a picture from your old textbook, or the old textbook. This one really demonstrates it more of this relationship between kinetic energy and potential energy. But here, when they're talking about potential energy, they're not talking about structure or chemical energy. Here, they're using a more common type of potential energy, which again is based on location, right? So in this cycle of events, this person here has the greatest potential energy that they're going to in this cycle, right? They're the highest that they're going to be. They jump off, right? Once they jump off, that potential energy is converted to kinetic energy as they're moving, right? As they're falling down with gravity, that's kinetic energy. Then they hit the water. That kinetic energy is converted to other forms of energy, one of which, as we know, is always heat. So even though you probably can't perceive it, when you smack the water, there's a little bit of heat put off. But also, when they hit the water, you can hear it, right? And when you can hear it, that's another type of kinetic energy, right? You hit the water, you smack the water, that vibrates the air around it, that hits your eardrum. That's another type of kinetic energy, right? The air is literally moving from them smacking the water. Of course, at this point, they have their least potential energy that they're going to have in this cycle. Then they start climbing up, and as they're using that kinetic energy to get higher and higher, they're gaining more and more potential energy, and the cycle continues. Of course, I'm not going to ask you any questions about diving off the diving board. Again, the idea here is to understand this relationship between potential energy and kinetic energy. They're not separate, right? So usually you use kinetic energy to build potential energy. Or sometimes you'll use kinetic energy, or you'll use that potential energy to create kinetic energy. So it's always a cycle, even when you're just diving into a lake or whatever that may be. So any questions about that picture? All right, if you download the PowerPoint, you can watch this little animation that talks about energy concepts. I love this concept. I'm going to be using it a lot, even though it's not in your textbook. So you're going to see pictures of bow and arrows and crossbows a lot, and you'll see why here in a second. So again, here's another energy you need to know about. Chemical energy, it is a type of potential energy. As far as the exam is concerned, it's the most important type of energy that we're going to talk about. Chemical energy. We will talk about light energy at one point when we're talking about photosynthesis. But even then, light energy is only used, well, twice in photosynthesis. But mostly photosynthesis uses chemical energy. Now, granted, that chemical energy got its energy from the light, but still, again, most of what we're going to talk about is chemical energy. And this is due to the arrangement of atoms. Another way of putting that is, like I've said so many times before in this semester, however much energy is used to build a molecule, that's how much energy will be released when you break that molecule. And not all molecules are created equal. Some molecules are harder to build. They require more energy to build them. Therefore, they release more energy when you break them. And I like these pictures right here. I don't remember where I found this. I didn't draw it, as you can tell, because you can see what it is. With my drawing, it wouldn't make any sense. But hopefully you can picture what's going on here, right? These two people are holding magnets. they're trying to push these magnets together, and what do you think's happening? Are they like trying to push it together and they're having a hard time, or are they trying to be sucked together and they're trying to keep them apart? What do you think's happening in that picture? Are they trying to keep them apart, or are they trying to push them together? The people.
We're trying to push them together.
Yeah, they're trying to push them together, right? And it's hard. It's not working because those two things repel each other. Same thing happens with cells, right? Or excuse me, atoms, right? We talked about the protons in the nucleus and the electrons on the outside, right? They're charged and they repel and attract each other in different ways. So again, however much energy is used to build something, they push those molecules together. They don't want to be together, those atoms. That is putting in energy. Same thing here, right? The crossbow, once you use kinetic energy, right, you're pulling that thing back, and however much kinetic energy you put in to pull it back until it clicks, like it is in that picture, now that is potential energy, right? That kinetic energy that you put in is now stored as potential energy. And I don't know if you guys ever shot crossbows or bow and arrows before, but generally speaking, the harder it is to pull back, the more powerful it is, right? Because it's requiring you to put more energy into it. Therefore, when you release the energy, there's more energy to pull back. Now, granted, there are things called compound bows, and that's where you use physics to use things like pulleys and stuff like that. But even then, even if you can't necessarily feel how hard it is to pull back, all those pulleys making it easier, there's still a lot of energy being put in there. Anyway, these concepts, especially that crossbow, we're going to come back to that idea. So any questions about what chemical energy is? All right, as I mentioned before, cells and engines use the same basic process to make chemical energy, stored in molecules or fuels available for work. We mentioned this, I think, chapter 2. It's the same basic concept. We have these molecules, these large molecules that have stored energy in them. We break them down in the presence of oxygen, and that energy is released, and we put that energy to use. And if you're driving, you put that energy to use by immediately turning that heat energy into kinetic energy, right? That helps your wheel, basically helps you move. And with cells, right, when you're, instead of burning octane, you're burning, in this case, you can burn a lot of stuff, but in this particular picture, fatty acids, right? When you break down those fatty acids, it's releasing energy, and that energy is going to be put to use. And that's what we're going to learn about in this chapter, is how that energy is put to use. There's a picture of what I'm talking about. This is not a picture from your textbook. This is the old textbook. But I love it because it really is kind of the same concepts, right? So again, we have a large molecule that we're breaking down in the presence of oxygen. And that chemical energy is then converted to kinetic energy. And of course, as you know, it releases heat energy, right? An engine gets hot because of that, right? You're releasing, you're converting it from chemical energy to kinetic energy. That's putting off heat. And of course, the byproducts of that are, amongst other things, carbon dioxide and water. And in our cells, similar things are happening. In this case, we're using glucose. Remember the last picture was showing fatty acids. But in this picture, we're talking about glucose. We're going to take glucose, we're going to break it down in the presence of oxygen. We're going to use that release of energy to make another type of cellular energy, which is called ATP. In the process of doing that, we're releasing heat energy, which is like, why do you think you're 98.6 degrees Fahrenheit? Because of this, right? It's all these chemical reactions happening in your body. That's why you are 98.6 degrees Fahrenheit. And of course, again, the byproducts of carbon dioxide and water. This whole picture is nothing but an introduction, so if you're a note taker, you don't necessarily need to write any of that down, because we're going to talk about it again later, especially the engine part, right? We're definitely not going to talk about that. That's just an example. So any questions?
I'm going back one song.
Not at all. This is also, so since you asked, as far as taking notes is concerned and studying is concerned, this is also not an important slide. This is kind of an introduction, getting us into this conversation we're about to have. So nothing to study here necessarily. Just an introduction. Like, all right, we're about to talk about breaking down fuels. And the textbook was just saying, before we talk about that, all these things you need to know, here's an example of how it's also similar to other things you're used to in real life. So, any other questions? Okay. Also a reminder too, these PowerPoints are all can be found on your WVSU online. So, cellular respiration. This is not in the textbook. And you definitely don't necessarily need to write any of this down except one thing, I'll tell you when we get there. Again, this is an introduction. I'm not going to ask many questions about what cellular respiration is, but there's going to be a ton of questions about how cellular respiration works. And You'll see what I mean when we get there. So yeah, cellular respiration is the energy releasing chemical breakdown of fuel molecules. That is the definition. You don't need another definition. There's going to be many, many questions about cellular respiration. Not one of them is going to be the definition of cellular respiration, or the definition of the word. So cellular respiration is breaking this down and then storing that energy, right? So you've got this chemical energy in the food you eat, and we're breaking down that food, we're releasing that energy, and then we're storing it in a form that the cells can use, that we're going to talk about later. And here's one thing you do need to know, so if you're a note taker, write this one down because it's not in your textbook. This is, again, one of those few times that I'm going to test you on something that's not in the textbook. About 34% of the energy you get from your food is converted to useful work, and the rest is just lost as heat. I guess I want to say lost, right? So it's, when we're endothermic or exothermic beings, we put that heat to use. So it helps keep us alive. But yeah, only 34% is used, right? So a lot of it is just not put to use directly. That's what this picture is. That's an infrared picture of somebody. So you can see they're emanating heat. Anyway, any questions about this slide? All right, the next slide is going to be confusing, maybe. So before I get into it, I just want to say I'm only including it because it's in the textbook, and I teach out of the textbook. This stuff that I'm about to show you is extremely unimportant for you as a student in this 100 level class. But if you were taking higher level science, there would actually be, again, chemical equations that this basically explain what we're about to explain. And these chemical equations use actual numbers. So if you were doing that, if you were doing these equations mathematically, then all this stuff would be important. But as far as we're concerned, it's not that important. First of all, there's this stuff called free energy. And in these formulas, it's represented by a capital letter G. And this quantifies the energy available for doing work after accounting for losses. That probably doesn't make much sense, but I'll come back to it in a second. And again, I'm not going to test you on what free energy is. Now, you will need to know the difference between exergonic reactions and endergonic reactions. So first, I'll give you the technical explanation. Then I'll give you the basic explanation, which is the one you need to know. So exergonic reaction. That means delta G is negative. Delta in these kind of equations means a change. So the change in free energy is negative in an exergonic reaction. What does that mean? That means it's releasing energy, which is kind of counterintuitive, right? That when I first started learning this, that threw me back a little bit. So I was like, all right, so we're releasing energy, but energy is negative. And if I had to, I would make that make sense to you, but we don't need to worry about that because you're not doing these equations. Another thing this means is the products have less free energy than the reactants. Another way of saying that is we start off with this high energy molecule or molecules, whatever, right? It's got a lot of energy. Then we break it down, we release energy, and now the reactants or the products, we start with high energy reactants. We break them down, we release energy. Now the things that are left have less energy stored in them, right? Because we released a lot of the energy by breaking it. So in other words, in a layman's terms, what you can think of for exergonic reactions would be like catabolic reactions, right? We're breaking things down. We're taking these high energy molecules, we're breaking them down, we're releasing energy. That's what you need to know for the exam. Exergonic reactions, releasing energy. Yes, I've explained the delta G thing and all that, but for you guys, that doesn't matter. Exergonic reactions release energy. You start off with these high energy molecules, you break them down, you release energy. Endergonic reaction is the opposite. Here, the delta G is positive, which again, I'm only mentioning it because the textbook does. You guys don't need to worry about that. But when we have a positive delta G, what that means is it takes energy to do it. So in this case, again, it's the opposite. Here, the products, right, the end product of this chemical reaction has more energy than what you started with. And these types of reactions are non-spontaneous, and they, again, require an input of energy. So, again, talking about what we talked about earlier, another way you could think of these as anabolic reactions. So endergonic reactions, we have these molecules or atoms. They have not too much energy, and then we're going to put energy into it to put them together, right? That's an energy input. We're building something. It's going to require energy to squish those things together. So now what we're left with when we're done is this molecule that has a lot of energy because we took a lot of energy to build it. So again, for the exam, this should be nice and simple. Exergonic reactions release energy because you're breaking things down. Endergonic reactions require energy because you're building things up. Now, regardless of which type of reaction we're talking about, they all require something called activation energy. And that's an important concept you need to know about, activation energy. So the next slide, after this, we're going to start talking about what activation energy is. The next word for attendance, again, has nothing to do with biology, is Hank. Because today is Hank Williams' birthday. Anyway, activation energy. This is the energy invested to start a reaction. And again, just like always, when I give you a definition, don't memorize it verbatim. Understand the concept. So what I'm saying for activation energy, right? Whether we're talking about an endergonic reaction or an exergonic, right? Whether we're talking about catabolic or anabolic, whatever it is, any chemical reaction, whether it's going to give off energy or take energy, still requires an input of energy. So even in a reaction that's going to put off a lot of energy, still requires a little bit of input of energy, right? And that's a very important concept. Because remember, the last thing we talked about was endergonic reactions, right? And I said that takes an input of energy. That whole thing takes an input of energy, right? You're going to be putting a lot of energy into an endergonic reaction. Exergonic reactions, remember, give off energy. And even those reactions that give off a lot of energy do require a little bit of energy to get it started. And that's what activation energy is. And I'm using, again, going back to this analogy. So you have all that stored energy in the crossbow, right? It's ready to go. And how do you release the energy from a crossbow? And it's obviously very obvious in that picture. How do you release energy from the crossbow? Yeah, you pull the trigger. And that requires energy, right? You literally have to, you're burning molecules in your cells to convert that energy into kinetic energy of pulling your finger. And it's not a lot of energy, but you put a little bit of energy in, and then you're releasing that energy, right? And then it shoots. So, again, that's what activation energy, right? You have to put in a little bit of it. And even, again, in this case, that's a lot of energy being released when you pull the trigger, even with a gun, right? You pull the trigger with a gun, the amount of energy you put in to pull that trigger is not even close to the amount of energy that's going to be released when that pin hits the primer and, that starts basically a small explosion with the gunpowder. It's a lot of energy being released by just a little bit of input of energy. That's activation energy. It's a very important concept. Here's a picture from your textbook. So here we have, this is the same chemical reaction, some generic chemical reaction. Here's the products, here's the reactants, here's the products. This is the same chemical reaction here. We start with the same reaction, end with the same products. We're releasing the same amount of energy. However, again, we still need activation energy, and this is what enzymes are for. Enzymes reduce the amount of input of energy, right? So you're still going to need some energy to get it started, but enzymes help to where you don't need as much activation energy. Because a lot of these chemical reactions that happen in your cells, it would require so much energy without enzymes, they just wouldn't happen. We wouldn't be alive. So without these enzymes, there wouldn't be enough energy. You wouldn't be alive, right? These enzymes help lower the activation energy. And again, using the same analogy, I don't know if you guys have ever shot a gun, and then maybe switched out the trigger to where it was a lighter trigger, like a feather trigger. It requires less energy, right? In that sense, that's an enzyme, right? You've changed it to where you just need less energy to put into it. Of course, you're still going to put out the same amount of energy, but now you need less energy to get that reaction started. So if you download the PowerPoint, you can also watch this little animation that talks about, I'm sorry, that's not an animation. That's just a really confusing picture, right? So if you're not a scientist, that might not make much sense to you. The point here is, in this case, we have an endergonic reaction. We have these reactants that don't have much energy. We're squishing them together. So now the products do have more energy. Again, I only included this because it's in the textbook, but the idea here is activation energy is the amount of energy required to start the chemical reaction. And that's it. We have a 10-minute break. We'll start lab at 9, all in the dot. And then once we get started, once you guys are started, I'm going to leave since I'm sick. Of course, if you're online, you need to go ahead and send me those attendance words before 9 a.m. If you're in person, you can send me them if you want for extra credit. Oh yeah, and of course, the last word for attendance, even if I forget to say it, is always to ask me one question about the concepts covered in this lecture. There you go. Hey, it recorded the whole time. It's a miracle.